All right, so we're going to dive into the technical materials today. The topic for today is search. What is search about? It's about agents that act intelligently by planning ahead. We'll look at what search problems are, and we'll look at a few methods to solve search problems, and we'll continue our coverage of methods to solve these problems next lecture. So what does it mean to be an agent that plans? Let's say you're an agent and you're interested in eating an apple. And the apple is up in the tree. Now, it might be that this agent has a command that just says, fetch apple from tree, and then all you need to do is execute that command, and that's it. But often, what you need to do will not be readily available as a single action. You might have to think about, well, to get the apple, I actually first need to maybe climb in the tree or jump high up. After doing that, when I'm close to the apple, I can grab it, hold on to it, bring it back down, and then I can start eating it. And so when there's a sequence of things you have to do, and you think about that ahead of time, what sequence you might want to act according to, that's planning. Now, before we get into planning itself, let's think about the opposite type of agents, reflex agents. What's a reflex agent? A reflex agent chooses their actions based on the current percept and potentially a memory of percepts. They can have a model of what the world is like right now based on their percepts, but a reflex agent does not consider the consequences of their actions. They don't think, what if I were to do this, what would happen? They just see what the world is like, see what percepts they get, and it directly maps to an action. Anybody has a good example of a reflex agent that they've seen in action or maybe are themselves over there? Roombas, depending on how they're programmed underneath, of course, but one way that some people think they're programmed is that they kind of just randomly move around and try to suck up dirt. That's a perfect reflex agent because you're not thinking ahead, you're just moving around and sucking up dirt. Another example where it's actually potentially optimal to have a reflex agent is, let's say you're a little controller sitting in somebody's eye, and when something is very quickly coming towards somebody's eye, you make the eye blink so, let's say, the insect doesn't fly right into the person's eye. That's a reflex agent. It's just saying, oh, something's coming. Let me close my eye to not be hit by it. And there's no thinking ahead. There's no time really to think, oh, what if I were to keep my eye open? Where would that little insect likely go? What's the better outcome and so forth? You just react instantaneously because you don't have time to think it through. Okay, let's take a look at some demonstrations of reflex agents in action. So, here, the first one we'll look at see if I can get it up there. There it is. So this is a Pac-Man board, and this Pac-Man is programmed to just move to the closest dot, so in the direction of the closest dot. So it sees a dot east from it, it moves east. So let's see what happens. Now the closest dot is north, west, south, and actually cleans the board in an optimal way, even though it's just using a reflex policy. Okay, now let's take a look at another scenario with the same reflex agent, but acting in a different environment. So we have, again, a reflex agent where it just takes the move in the direction of the closest dot. Let's see what happens. It's cleaning the board pretty efficiently so far. And now it's saying east, 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 east. One thing you notice, its score keeps going down. This is not a standard Pac-Man game thing. This is the modification we make in 188, where every time step that passes, you lose 1 point. So sitting there and doing nothing, things get worse and worse and worse for you. But that's what a reflex agent is. It has its limitations. It doesn't think ahead. It doesn't realize that nothing's going to happen by taking the action east, and it just keeps trying that action. All right, so clearly reflex agents have their limitations. But as we discussed earlier, sometimes they can be optimal. They can be optimal, let's say when you're closing an eye for an insect that's coming. They can be optimal when the scenario is so simple that the reflex policy happens to do the right thing. Okay, so actually one thing I want to note is that for the slides, we make them available on the website. We make available PDF versions, 1 per page, 2 per page, 4 per page, 6 per page, whatever you prefer to work with. We also make the PowerPoints available. The PowerPoints have videos of the demos I run in class. So for example, this slide here has a video of the demo we just ran. So if you want to watch these demos again, in the PowerPoint slides, you can watch them again. Of course, you can also watch the webcast, but there are different options there for you to watch them again. Okay, so planning agents are agents that ask what if. So they make decisions based on simulating in their head, if they were to take a sequence of actions, what would happen? And they would, in their head or inside a computer, simulate many different sequences of actions to find one that they prefer. And then, once they found one that they like, execute that sequence of actions. So it's all about thinking about how the world would be if you were to act in a certain way. Now, when we think of planning, there are a couple of properties planners can have. A planner could be optimal, which means that it finds the best solution to the problem that you're posed. For example, for eating the dots, it could be the solution that is the shortest path to eat all dots. A complete planner is a planner that, if a solution exists, it will find it. And then there's a distinction between planning and replanning, which we'll get to in this next demo here. But let's first take a look at an optimal planner. So what we're going to look at here is a Pac-Man mastermind agent, meaning this is an optimal planner thinking it through very carefully. And let me also bring in the console here because it'll show what it's thinking about at the bottom here. Okay, so let's get this one started. So it's pre-calculating, it's doing some computation, still pre-calculating. It's done with the pre-calculation. Now it's doing some regular calculation. It's done 1,000 of them. 2,000. Now it found the plan, which is the optimal plan. It's executing that plan. It actually knows that you should go first far away and do the dead end last. And it finds the best way and executes it to clean that board. But it requires a lot of thinking. So this is good if your problem is solvable in a reasonable amount of time with an optimal planner. Now often what will happen is that you don't have that time. And so what you might want to do then is replan. And what I mean with that is you, instead of solving the original problem of cleaning the entire board, you solve the problem of finding the nearest dot, which is a planning problem in and of itself. You need to find a path to the nearest dot. Then you execute that path. Then from there you find a path to the nearest dot. And so you're continuously replanning for the next sub-goal. So let's take a look at that. So let's move Pac-Man into your view. So here we are. Again, at the bottom in the console, you'll see the thinking happening. So it pretty much instantaneously finds a path to the nearest dot and then executes it, keeps repeating this. There's not this thinking phase, but now it doesn't find the optimal solution because it has to go back and forth in that dead end, but it finds a solution much faster. And so it depends on the type of problem you're faced with, what might be the desired way to solve your problem. All right, so these are the videos of the demos we just saw. So let's start taking a look at how we formalize these problems. So search problem consists of a few components. And this will be a common thread, by the way, in this class, is that we're not going to formalize here how to solve Pac-Man. We're going to formalize something general. What is a search problem? That is applicable to Pac-Man, but just as well to other applications. So the first thing you need is a state space. What's a state? A state is a possible configuration of the world. Then a successor function. A successor function describes for each state and each action you could take in that state what the consequence would be, what the next state will be after taking that action. There could be cost associated with this. So there could be a number that says this is how much it costs to take this action in this state. So you could start in a state, and then there are, in this case, there's an action north and action east, and then the successor function knows what the possible consequences are as a function of the action. Then there's a start state. This is where you are right now, what the world is like right now. And then there's a goal test. And the reason it's goal test rather than goal state is because there could be more than one goal state. It might be, for example, if the task is to eat all the dots, you're happy for Pac-Man to end up anywhere on the board at the end as long as all the dots have been eaten. And so every different location of Pac-Man would correspond to a different state, but all of the ones where the dots are all gone are satisfying the goal test. A solution to a search problem is a sequence of actions that gets you from the start state to a goal state. An optimal solution is one that does it with minimal cost. Okay, so first thing we have to do then, of course, if we care about solving problems in the real world, is to model real-world problems as search problems. Okay? One thing to keep in mind here is that that's often in practice a lot what you'll be doing. Even though we'll spend a lot of our time on algorithms in this class, these algorithms are in some sense pretty well known by now, and probably you download an implementation if you implemented it in a large-scale infrastructure. But understanding how your real problem becomes a problem that your algorithm can solve is what you would be solving when you're solving real problems. So let's take a look at an example. Let's say you want a route. This is a map of Romania. Let's say you start over here in Arad, and maybe you want to get to Bucharest, right? So this is a planning problem. We want to find the path. But one thing to think about here is at what level of abstraction are we going to solve this problem? One way to solve this, think about, well, I might need to get into a car. I might need to then start the ignition. I might need to put my foot on the gas pedal. I might need to change in reverse, back to forward. I might need to make a turn. I might need to avoid other cars and so forth. That would be a very detailed plan. And it's reasonable to think of planning at that level. In the example we're looking at here, we're going to plan at a more abstract level. We're going to think of it as a sequence of cities we go through to go from the starting city to the goal city. In practice, you would then refine that plan to execute on it, and you'd make a new plan for every step. So what does the search problem look like? A state space, since we're going to plan at the level of cities, the cities will be the states where you're currently at. The successor function tells you essentially the outgoing edges from each city and which other city they land. So the roads. The distance between cities could be the cost, but alternatively, you could decide that the expected travel time on any of these roads is your cost, depending on what you tend to optimize for. The start state is where we start, so that's a rod. Then the goal test, in this case, there's only one goal state. It's whether you are in Bucharest or not. So the test is the state equal to Bucharest? And the solution would be some path that gets us from Arad to Bucharest, maybe this path over here, that's one, but there are other ones. Let's look at other examples. So let's again make that distinction. There's a concept of world state, which is what the world could be like, which involves all the details of the situation, and there's the state in your program that is used in the search. Okay? So the world state for this Pac-Man problem would include everything. It'd be where Pac-Man is, where the dots are, where the power pellets are, where the ghosts are. Anything that can change over time will be part of the state. Anything that's fixed, you don't need to put in the state, that's just a constant. Now for your search problem, it depends on what you're trying to solve, what will go into it. Let's say in the first example that we're looking at pathing, meaning we just want to route Pac-Man from a starting location to a goal location. And we're not worried about ghosts, anything like that. We're not worried about eating pellets. We just want to go from a start to a goal location. What would be a reasonable state space? Any thoughts? Over there. So the answer was Pac-Man's location. So a reasonable state space would be just the x and y coordinate of Pac-Man. We need more than that. We need a successor. Yes? Succession over there.
Pac-Man's location along with location of all the dots on the board.
So one suggestion is include also the dots. Would that still work? Well, the principle you have to go through here when you think about what should go into the state is, well, how do we solve these search problems, right? What do we need to define a search problem? We need to define a successor function that tells you for every action you take in a specific state, what's the next state, right? And if we represented a state as x, y, and where the dots are, and we took an action, we could represent what happens to the coordinates and the dots. If we just represented it as x and y, we took an action, we could represent what the next x and y coordinates would be. So both of these are compatible with being able to define a successor function. How about the goal test? So the goal test checks whether Pac-Man has reached a goal location, in this case, the particular goal location. For that, we only need x and y. We don't need the dots, because we're just solving a pathing problem. So what that means is that we actually, for the goal, after checking for goal, we don't need the dots. Can we leave out the dots? Well, we know that we can have a successor function with just x and y. We can have a goal test with just x and y. So we actually just need x and y. If you included the dots, it would still work. But it might slow down your algorithm because it will consider a larger state space. And so often the exercise is one of finding a small enough state space, as small as possible, while still being able to solve your problem. So in this case, we would not consider the dots part of the state space for an efficient choice of state space. Yes?
Do we also have to consider where the walls are?
So that's a great question. How about the walls? Should we put where the walls are in the state space? Because it'll affect the successor function, right? And so the way we define state space is we only look at the things that can change. So if the walls are fixed throughout the entire game, the wall configuration would be passed into the successor function as a constant, and it wouldn't be a variable. So we need it, but it's not a variable, and so we don't consider it part of the state. Now, of course, if you change the game and Pac-Man can blast through some walls every now and then and make them disappear, then it becomes part of the state space. Okay, so we solved the first one. Here's another one. What if the problem is eating all the dots? What would be a good state space now? Again, what do we think about? Can we have a goal test based on that state space? And can we have a successor function? Any thoughts on a state space? Over there. All the locations of the dots, you want that in your state space, because otherwise you're not going to know which one have been eaten, which one not, right? You also want the location of Pac-Man. So a natural choice would be here location and all the locations of the dots that are still there. Just to throw something out there, would just keeping track of the number of dots left be enough, rather than keeping track of the locations of all the dots left? It'd be enough for the goal test, because once it hits 0, you know you achieved the goal. But it wouldn't be enough for the successor function, because if all you know is the location of Pac-Man and the number of dots left, when Pac-Man makes a move, you cannot compute whether that number has decreased or not, because you don't know where the dots are. All right, so here we'll go with x, y coordinate for Pac-Man, and then booleans for each location, whether there's a dot there still or not. Actions remain north, east, south, west. Successor function does the right update, and the goal test is whether the Boolean values are false for all dots. So I said earlier, we like to keep state spaces small. So let's take a look at how big they can be. Was a question there?
Oh, yeah. When you were saying to use maybe the number of dots instead of the locations of dots, couldn't that work with planning? Couldn't we tell Pac-Man to traverse just every space until maybe it reached the goal state?
Okay, so here is the suggestion here is, in some sense, since we know there's a dot at every spot, maybe we could define the problem as you need to have traversed every location in the maze, and once you've done that, you satisfy the goal test, right? So that'd be a reasonable way to formulate this exact same problem. Now, to check your goal test, you need some information of what has been traversed by Pac-Man. So you'll need to put something in the state that keeps track of where you've been, where you have not been, which will essentially be equivalent to tracking whether a dot has been eaten or not, but it'd be equally good, absolutely. So let's look at sizes of state spaces. So the world state here in this board, there are 120 locations Pac-Man could be at. There are 30 food pellets. There is 30 booleans there. 12 possible ghost positions for each ghost, and the agent could be facing north, east, south, or west. Okay, so what's the size of the state space? How do you count this? Right? For every variable, you need to see how many values it can take on. So the first one is agent positions, 120 values. Is that showing up? No. Okay. Then we multiply with the number of values the next variable can take on, where there is still food. So keeping track of the food takes 2 to the 30, because for each of these 30 food pellets, it could still be there or not be there anymore. Then each ghost could be in any of 12 positions, so that'd be 12 to the 2 to count for that. And then the agent could be facing any of 4 directions, so times 4. So just, especially this thing over here, makes this number very, very large. And this is a small problem in the grander scheme of things. It's a pretty small board, yet because of these food pellets that could be on or off, the state space very quickly explodes. Okay, now how many states do we have? So world states we did. That's written down here again. If we look at the search problem of pathing, question there. Okay, so the way we counted that is that there are 12 possible y coordinates and 10 possible x coordinates. And so 10 times 12 is giving us 120. Okay, so Pac-Man can actually sit between those dots. So not every spot is occupied by a dot initially in this board. So if we're just doing pathing, we know our state space is just the location of Pac-Man, so we're just left with a state space of size 120. And leaving everything else out is going to be very beneficial. If we're looking at the problem of eating all the dots, well, we can still leave out the direction the agent is facing because it doesn't affect how they can move. You can still leave out the locations of the ghosts because they're isolated anyway, and you're left with this first part over here, which is still pretty large, but at least smaller than what we started from when describing the entire world. All right, let's do a little quiz here. So the problem we're looking at here is a Pac-Man problem again. We want to solve the problem of eating all the dots while keeping the ghosts scared at all times. What does it mean for a ghost to be scared? When you eat one of those big, wide pellets, the ghost gets scared for a certain amount of time, after which they get unscared. So you think of this, essentially, the solution is going to involve something where by the time they're about to get unscared, you need to have eaten another big, wide pellet, which is called a power pellet, to make sure they're scared again. But the question we're asking here is not what does the solution look like, what does the state space look like for the problem of eating all dots while keeping the ghost scared? Let's take a minute for you to think about this, talk with your neighbors, and then let's see what you came up with. All right, let's see what you came up with. Any thoughts? Anybody who wants to take a stab at specifying the state space? Over there. Could you repeat that? So the coordinates for Pac-Man, the dots, for each one of them a Boolean, whether it's still there or not. And then for each power palette, a Boolean saying whether it's still there or not. Okay, any other thoughts over here?
Well, with that, would you need something like how much time before you need a new power palette?
So the suggestion is to add something related to time, some kind of timer. Maybe that's counting down how much time you have left. Any other thoughts over there?
Maybe the location of the ghost in case you eat one of them and he comes back.
So I'm going to put this separate here. Location, ghosts. So this one here depends a bit on how you define the problem. If we assume that ghosts respawn as unscared once you run into them, we need this because you kind of want to avoid running into them unless you're right next to another power pellet. If we assume that when you run into a ghost, nothing happens, it just stays scared, then we don't need that one. But overall, this seems right to me, so let's sanity check. Can we run a goal test? Can we check whether every pellet has been eaten? Yes, because we keep track of it. How about a successor function? For any state, written as it's provided here, can we compute the next state when we take an action? Sure, if we take an action in any direction, we know what the new coordinates will be. We can compute that. We can compute whether there's an update to the dot booleans, to the power booleans, and whether there's an update to the timer, which normally will go down by 1, but if you ate a power pellet, it'll be reset to a higher value. So we can have a successor function with this state space. Could we make it any smaller? Not clear how we could make it any smaller without losing something that we need to solve the problem. Now, one thing that's interesting here is that keeping the ghost scared sounds like a goal, right? It's like one of our goals is to keep the ghost scared, but it's actually not part of our goal test. It's encoded in our state space and in our successor function, right? If ever the timer would go to 0, and we would not be able to eat a power pellet, essentially that would be a dead end of that possible sequence of actions, because at that point, there's nothing available. The successor function would say, this is not extendable, this sequence of actions, because from this point, there's no action that keeps ghost perma-scared, and so your search would stop down that possible simulation and say, this is not possible, and find other possible sequences of actions. All right. So we've talked a lot about search problems. Now start thinking about how we'll solve them. So the first important distinction is the one between state space graph and search trees. And this terminology will be important, and we'll spend a little bit of time on it right now. So a state space graph is a mathematical representation of your search problem. So let's say you're doing some Pac-Man food eating problem. It'd be all possible configurations of Pac-Man and food pellets. This graph is bigger than what's shown on the slide. It runs beyond that. It shows how you can transition between states and which states exist. Okay? These can still be abstractions of what's really happening in the world. They are whatever you're going to use in your search problem as your state. Arcs are successor functions, effectively, or correspond to them. And the goal test corresponds to a set of nodes in this graph that are goal states. Okay, in a state space graph, each state will occur only once. There's no repeat occurrences of states. Rarely can we actually build up this graph in memory. This graph is interesting to think about, to know that it exists, to reason about, and for really tiny problems, we might be able to show them on a slide, like we did over here for a really tiny problem. But for any problem you realistically care about, you'll never see that state space graph. Because if you could look at it, you could probably solve your problem by hand and wouldn't need a computer program to solve your problem. Okay? But on these slides, we'll often show a state space graph just to illustrate the concepts. This is the example we'll usually work with, this graph over here. Okay? So a lot of the game that we're after here will be to effectively reason about this state space graph without ever fully building it. We want to somehow find a solution in this graph without building the graph. So how would we do that? A search tree is a structure that we use for that. The search tree is rooted at the start state. Then you can call your successor function, see what actions are available, and for each action what the next state is. Those are the next two nodes in your search tree. And from there you can repeat, and that's how you can build up your search tree. Now, search tree essentially encodes all possible sequences of actions. If you go down a path in your search tree, that corresponds to a possible sequence of actions. Okay? Now, for most problems, again, you cannot consider the entire search tree. It'll be really, really big. In fact, it'll even be bigger than the state space graph. And so the game will be one of finding a path that gets us to a goal state in the state space graph without ever constructing the state space graph, but instead working with the search tree, but again, not the entire search tree, but just part of it, the part that we need to find a solution. Okay. So let's contrast some things here. So here's our tiny, tiny state space graph for this pathing problem. There's a start state here, there's a goal state here, there's only one goal state in this case, and in red there's a path marked that is a solution. On the right here, we see the corresponding full search tree. So it starts with the start state, and then its three neighbors, D, E, and P, are next, and from there it keeps branching. These are directed arcs here, and because they are directed, at some point things stop. If they were undirected, meaning you could go in both directions, this search tree would go for a longer time. Okay, so let's ask you a little question here. This is a four-state graph. On the left, we have the state graph. What is the search tree for this state space graph? Any thoughts? And in particular, how large is the complete search tree going to be? Any thoughts? How many nodes in the complete search tree? Okay, we can actually try this out, right? You start at the start state. You could go to A or to B. From A, you could go to G, or you could go to B. From B, you could go to A, or you could go to G. A, you could go to B or to G. B, you could go to A or to G, and so forth. And then we haven't even started here. You could go to A or G, and so forth. So how many nodes in the search tree? Infinite. So a lot of repeated structure in this search tree where we have this branching on the same state. We'll in next lecture see how to resolve that kind of problem, but for now let's not worry about it and just know that that's the search tree. Okay, so tree search is all about somehow exploring only part of this tree. So let's look at an example. This is the Romania search problem. Starting in Arad, wanting to end up in Bucharest. What does the search tree look like here? Well, we start with Arad at the top of the search tree. It branches to 3 cities, so we can put those 3 cities down. Then from there, they branch, each of them. Oh, that's too fast. And so as you build your search tree, effectively how you build it up is by keeping track of what's called a fringe. So initially, the fringe is just this start state. Once you call it successor function, see what's possible, you now have these 3 states in what's called your fringe. It's the frontier of your search tree. And then we expand this one, so that one gets booted out, and its successor function will instead add these into your fringe. So at the end here, we're left with a fringe that looks like this. Okay, so let's build an algorithm out of this about incrementally building up this search tree. So it's called tree search. It takes in a problem and a strategy. We'll talk about strategy later. A problem is a search problem. So a start state, a goal test, a successor function. We initialize the tree with just the initial state, the start state of the problem. And then we go in a loop, where we keep going around until we exit because we found a solution or a failure. So the first thing we do is we check if the fringe has anything left. If somehow the fringe is empty, we have no way anymore to expand the tree. We're done. We return failure. Now, when we start, of course, there's one node in there. This will not happen. It will be not empty. Then we choose one node from the fringe. Initially, there's only one choice, but in the future, there will be more choices. You choose that node according to your strategy, which we don't know yet, but you pick one of the nodes, expand it. Actually, you pick one of the nodes, you check if it's a goal state. If it reaches a goal state, you're done. You return the solution. If it's not a goal state, if it doesn't lead to a goal state, more precisely phrased, then you expand that node by calling the successor function and then go back around in the loop. Okay, so what are the main ideas here? There's a fringe, which is this set that keeps track of nodes that you still want to expand. There's a concept of expanding a node, and there's a concept of a exploration strategy. Okay, which one do you pick? So let's do this, and you guys will get to pick which one we expand next. So let's put our search tree here. And let's put another representation, the queue-based representation here, which might be closer to what you might have in code. So the search tree starts with just S. The queue will start with just S. Okay, we'll do expand S, only option. So expand S in the tree, that means we add this branch to D. Keeps going away somehow. Oh. It's showing for me, but not for you guys for some reason. Let's see. So there's D and P. In the queue, the way that will manifest itself is that S is removed from the queue, and instead we'll have S to D as a potential plan, partial plan, and S to P. Is there another one? Oh, thank you. S to E, and that will be added to the queue also. Okay, so now we have a choice, D, P, or E. What's your pick? I'm hearing a lot of D. E? A lot of E. All right, let's go with E. This one here. We expand E, which can lead to H or R. Over here, what that means is we scratch this one out, and instead we have S, E, H. Oh, come on. That's not where we want to be. S to E to H, S to E to R. Okay, which one do you want to expand next? R. So from R we can go to F, or that's it actually, just F. So this one will be removed here, and we'll have S, E, R, F. What do you want to expand next? I hear F. I'd agree with that. Oh. So we expand F, which leads us to the goal. The one with F will be gone here, and we'll have, oh, don't erase. S, E, R, F, G. Now remember, we're still in our algorithm. We go around. Which one do we want to choose for expansion next? G, right? We pick G. We check if it satisfies the goal test. It does, and we call it done, and that's the completion of our search. Okay, so that's the complete algorithm. The strategy here was you have an entire lecture room of people saying you what to do. The rest of the lecture will look at how you can code up a strategy when that's not available to you. So the first one is depth-first search. What's depth-first search? Okay, well, in depth-first search, the way you expand is by always going deeper in your search tree. So you start with just S on your search tree. You expand, you get a new fringe with D, E, and P. Then here, all of them are equally deep. So you break ties, let's say left to right, so we go with D. Now we have three that are equally deep and deepest, B, C, and E on the left there. Again, we break ties left to right, so B will be expanded next. And we kind of keep working our way, deepest first, breaking ties left to right through the search tree until some point here, and we're not there yet. G is now sitting in our fringe, but it's not picked for expansion yet. We keep going, and finally we pick G for expansion. We realize it's reaching the goal here, and we're done. Return that solution. So that's depth-first search. Let's take a short break here, and then let's study properties of this algorithm after the break. All right, let's restart. So we just looked at our first strategy, which was depth first. Now let's take a look at what types of properties we might care about for each of our search algorithms. So the first one is this algorithm complete? Is it guaranteed to find a solution if one exists? Yes and no. There's a little caveat here. If your search tree is such that it's infinite, and the leftmost path in your search tree is infinitely long, then you would keep going down that path, and if the goal is not along that path, you just keep going forever, and it would never return a solution. Okay? So it's not complete as stated, but with a minor tweak, we can make it complete. All we need to do is to say, if you already visit this state, then don't go down that path again because you've already seen it. But as stated right now, it's actually not complete. Is it guaranteed to find the least cost path? No, it's not even considering cost. It's just gunning down the leftmost path in the search tree and see where it first finds a solution. How about the time complexity? How long does it take? Actually, let's illustrate this one on the next slide. So another question is time complexity and space complexity. So for this, let's draw a cartoon in terms of what we care about. When we start looking at complexities, we need to somehow characterize how long something takes as a function of the size of the input. Right? So we need to put down some numbers that characterize our search problem and say, well, as a function of those numbers, how long will it take to run? So the search tree would look something like this. There would be something called a branching factor, which is the number of successors you can have from any given state. That's B. Okay? So you start with one node, then have B nodes, then you have B squared nodes in the next layers. If you have M tiers, at the very bottom, you'd have B to the M nodes. So even though this just kind of looks like it's growing linearly, really this is exploding exponentially as you go towards the bottom of your tree. Okay? Another number then is M, which is the maximum depth. So that's however deep your search tree ever ends up being. It could be infinite, but for other problems it could be bounded, and then there is a finite number M saying how deep your search tree is. Okay? There could be solutions at all kinds of depths, right? We can consider counting how many nodes there are in the entire tree. One thing to keep in mind there is that it's essentially dominated by this bottom layer here. That bottom layer has so many more nodes than the previous layer, which has so many more nodes than the layer before, and so forth. Now, there's roughly b to the m nodes in the entire tree. It's slightly more than that, but not a whole lot more. So order b to the m nodes in the entire tree, and b to the m in the last layer. Okay, so now we have this notation down, we can start thinking about time complexity and space complexity, specifically for depth-first search. So what nodes will be expanded by depth-first search in this search tree? It will be all the nodes that in some sense are to the left of the first goal that you can find. And so in this case, it's gone down all those directions in the search tree, and until it finds that particular goal, it will keep going. And so the entire gray shaded area will have been explored. So some left prefix of the tree. It could process the whole tree if you're very unlucky and that one and only goal state is sitting all the way on the right far deep end. You explore the entire tree. So if m is finite, this will take time order b to the m. If m is not finite, then this will take potentially infinite time. How much space does this take up when you're running it? So think about what's being maintained. As you're running this algorithm, you have this fringe. This fringe stores nodes that are still up for expansion. These nodes are all partial solutions or potentially partial solutions. They're a sequence of nodes that you could traverse that may be extended into a solution as you go along. And so that's what you're storing. So the question is, how large could your fringe be as you are running this search? Any thoughts? Well, let's go one step back. Let's say you're running this search. You're here. At this point, what's on your fringe? What would be on your fringe is these nodes over here would be on your fringe because you haven't expanded them yet, and they're the next candidates for expansion. If now you were to expand, let's say, the first one over here, you'd get a bunch of new ones on your fringe in addition. Then you expand the first one, you get a bunch of new ones on your fringe in addition. What you see is at any given time, at any level in that tree, you'll have at most b nodes on your fringe from that level. There are m levels, so you could have at most b per level times m is b times m nodes on your fringe. So that's the space complexity. Is it complete? Well, it really depends on whether your search tree is finite or not, right? If it's finite depth, it'll be complete. If there's a solution, at some point it'll have traversed the entire tree, worst case, and have found that solution. Of course, if it's infinite, you need to do some cycle checking. We'll get to that later. Is it optimal? We already said that. No guarantees of optimality. Okay. Leftmost solution is the best we can say here, so I guess it's great if your optimal solution is sitting all the way on the left, but otherwise it's not optimal. Question?
For the space complexity, why do you need to expand the other two? Or in your diagram, you have like each one goes down 3, right?
Yes.
Why do you need to have those other two in storage? Can't you just go down the first one and then generate the other two on demand after if the first one doesn't return a result?
So the question is, can you generate these extras sitting on there on demand? That depends a little bit on how things are set up, right? So the first time you go down, of course, you're going down just the leftmost path. You would be going down this way, and you would have expanded all the nodes sitting there. When your algorithm is, in some sense, backtracking, is going back up because it didn't find a solution, it needs to know at this previous layer here which options still need to be considered, right? So it needs to somehow know which other successors still need to be explored, right? And so one way to do that is to place them on the fringe as you are in this node, and you call the successor function. Place them there. And sim, as you go back up, you always want to keep track of which directions haven't been explored yet. And if you don't explicitly keep track of, you can either keep track of what you've already seen, or you can keep track of what you still need to explore. You need to do either one. typically, in this algorithm, that's what we do. You keep track of what you still need to look at, because the things you still need to look at in this kind of way of keeping track of things is typically going to be smaller than everything you've already looked at, because you'll have looked at maybe the entire tree at some point. Question there.
Yeah. A question on how much space it takes to store one fringe case. Let's say we're looking at the leftmost all the way down, and then we go one to the, I guess, middle. Shouldn't that fringe have a size of m because of how many nodes it?
So we said how many nodes could be on the fringe, which was b times m, right? And then your question is, how much space is taken by a single node that is sitting on the fringe? It depends on your type of implementation. A most straightforward implementation, a single node could be m states in sequence, or m actions, because your tree is m deep. So then the memory complexity would be b times m nodes times m per node. If you store this in a data structure that effectively uses back pointers, you would not be storing that extra information in as redundant a way that as we just described, and it would come down to b times m. So it depends a little bit on the details of your implementation. But you're absolutely right that you need to consider how you store each of those nodes, and they need to contain a way to understanding not just the last state, but the entire path they encode from start to current state. All right, so let's switch strategies. Breadth first search. So how would that operate? You start again with just your start state. You call the successor function on that one state in your fringe. Now you have a choice out of 3. They're all equally deep. Breadth first picks the one that's least deep, but they're equal, so you break ties left to right in this case. How about now? Here's where it becomes different from depth first search. E and P are least deep. The E and P over here, we break ties between them left to right, expand E. Now P is the least deep one, expand that one, and we keep repeating this process. So you go tier by tier horizontally through the search tree until at some point what you expand is a state that reaches the goal, at which point you're done. Okay, let's look at its properties. So what nodes does it expand? If the search tree pictorially looks like this, where the red dots are goal states. It'll explore everything till that tier where the first goal state is, the most shallow goal state. So it'll keep going down in tiers until it's there. And the grayed out part is what it explores. So, okay, we can then say, let's call S the shallowest depth where there is a goal. Then the complexity of breadth first search, the time complexity, would be b to the s. Because that's the number of nodes sitting in that grayed out part, order b to the s. How much space does the fringe take in breadth first search? Okay, so what is sitting on the fringe at any given time? Let's say you are in this tier over here. What's sitting on the fringe right now? All nodes at this level are sitting on the fringe. And as you work your way down tier by tier, essentially you'll get something where at the next stage you'll have a fringe that looks roughly like this, and so forth. And we'll kind of creep left to right to fill in the next tier, get rid of the previous tier. So how many nodes are sitting there? Well, depends on how deep you are, but it's order branching factor to the power your current depth in your search. We go as deep as S, so the space complexity is order b to the s. Is it complete? If there is a solution with finite depth, it'll find it, assuming some finite branching factor, of course. Is it optimal? Yes and no. It's optimal in the narrow sense that if you want to find a solution that takes the smallest number of actions, it'll find that. But if your actions don't all have equal cost, it's not considering the cost of actions, and so it's not optimal in the kind of most general sense of optimal. All right, so Let's think about when we might prefer depth first search versus breadth first search. So when will breadth first search outperform depth first search? Well, if you care about a solution with a smallest possible number of actions, breadth first search will give that to you. If your solution is sitting pretty high up in the tree, then breadth first search will find it more quickly than depth first search, most likely, unless it was all the way to the left, right? When will depth first search outperform breadth first search? That's a trickier one. When would that ever do better? Well, a big thing is the space complexity, of course. Breadth first search might run out of memory, and then it just stalls and nothing happens anymore in your computer, whereas depth first search uses a lot less memory. Sometimes your problems are such that every plan will have the same number of actions. And then it doesn't matter that you tier from top down like breadth first search does, because all the solutions are at the bottom. And then depth first search might be quicker because it always guns straight to the bottom and explores things at the bottom. We'll actually see that when we look at solving constraint satisfaction problems, where the solutions will all be at the bottom of the search tree. Okay, let's do a little kind of game here. So I'm going to move this into my view to not give it away to you. Okay, what are we looking at here? This is a search problem. The green spot is the start state. The red spot is the goal state. You can move northeast, southwest. And I'm going to run a search algorithm. You're going to say which one it is. Okay? So this is breadth first search. It fans out from where it starts, looking at things that are equally far away from the start state. So a dot that appears means that it's looking at that state to get there. Then let's clear this board. How about this one? Depth first search. The leftmost solution was found. Okay, so we'll do some more of these quizzes when we have more algorithms to choose between. Now, one question you might ask yourself, can we get the best of both worlds? Breadth first search was this nice thing where if you wanted to find the shortest possible sequence of actions, it'll find it for you. The time complexity is less if the solution is not at the bottom. But then the memory complexity is worse. Is there a way to run a breadth first search with less memory usage than the naive thing we've talked about so far? There is. There's something called iterative deepening. And the idea here is that you effectively embed a depth first search inside the breadth first search. So how do you do that? You run a depth first search, but you don't search deeper than depth 1. If you found a solution, great. You return that solution. If you didn't find a solution, now you again run depth first search, but you never go deeper than depth 2 in your depth first search. If you found a solution, great, you return it. If you didn't find a solution, you can now run for depth 3. And so by repeatedly running a depth first search with a depth limit, you get the kind of behavior of breadth first search, exploring things tier by tier by tier, but the memory complexity of depth first search. Okay? You might say, well, isn't that wastefully redundant because the top tiers will be explored multiple times, because when we go from depth 1 to 2 to 3, we'll repeat the top part of the tree. The answer is yes, it is wasteful, but it's actually not as wasteful as you might think. Because of the properties of this search tree, they grow exponentially in size. So effectively, all the work is done at the bottom anyway. And so when you go from one tier to another one, it's negligible. The early work that you repeat is negligible compared to what you're going to add to it in this next round of depth. Now let's switch to cost-sensitive search. What do I mean with cost-sensitive search? We'll add cost to each of the arcs. So here's a new graph. Each of the arc has a cost associated with it. We want to find a least cost path. Right. Not just any path to the goal, the one that the total path cost is lowest. So we'll look at an algorithm called uniform cost search. It's probably the most confusing name of an algorithm that we'll cover in this class. Uniform cost search doesn't mean all costs are uniformly the same. Doesn't mean that. It means something else. It means the algorithm we're about to cover. Okay, so how does that work? You still have your search fringe. It starts with just the start state. You only have one choice. You call the successor function. Well, you check if it's the goal. It's not. You call your successor function, add things into the fringe. Now you have a fringe of 3. You look how expensive it was to reach each of those 3. You check which one is cheapest. Pull that one out. Check if it's the goal. If it's not, you call the successor function again. P is cheapest. Call the successor function. Add the successors to the fringe. Again, you check which one is cheapest on the fringe. It's D with a cost of 3. Is it the goal? No. Let's call the successor function. You keep repeating this. Work your way through that search tree that actually never exists, but you're kind of conceptually working your way through. Now, here it gets interesting. We have a fringe with a few nodes at this point. F is cheapest. Now, what's happening here? We have several nodes on the fringe, including one that reaches the goal. Keep in mind, the algorithm doesn't declare victory yet. It says, what's next from the fringe? Cheapest, which is E with a cost of 9. Grabs that one from the fringe, checks if it achieves the goal. Doesn't, so it calls successor function. Now the cheapest one is the node that reaches G. It gets checked for the goal, and we declare victory. It actually matters to only declare victory when the goal is the cheapest thing on the fringe. Because otherwise, if you right away declare success when there is a goal on the fringe, but there are still cheaper things, it's possible that expanding those cheaper things could very cheaply lead to another goal, and you would have declared success too quickly. So keep that in mind. You can only declare success when the goal is the cheapest thing on your fringe. It means you're out of cheaper options. Nothing exists anymore that could be cheaper. Okay, so it tiers it a bit like breadth first search, but the contours are different. They're by cost, not by vertical level. What are the properties of uniform cost search? Let's take a look. What nodes does it expand? Well, it expands all the nodes that can be reached with a cost less than the cost to reach the optimal goal node, right? And so we'll call C star the cost to reach the optimal goal. And if the minimum cost per step is epsilon, then that goal could be at most C star over epsilon deep. And so the number of layers you could go deep is C star over epsilon. That's the depth you might have to encounter. And so the complexity is based on that. It's branching factor to the power, however deep you might end up going, which we compute as C star, cheapest cost to reach a goal, divided by epsilon, which is the minimal action cost. You can already see if the minimal action cost is 0, this could still expand many, many nodes, because with 0 cost, you could keep going. If there was some kind of path that has 0 cost everywhere, you could keep going forever, because you'd always pick that 0 cost direction. If there's no goal there, it runs forever. Okay, how much space does it take? Well, this is a lot like breadth first search, right? It's just now measured by cost rather than tiering. So it's essentially the same equation. Branching factor to the power, however deep you might go, which is C star over epsilon. Is it complete? If there's a solution, will it be found? Yes, assuming every action cost is at least some finite amount away from 0. Is it optimal? We won't prove it right now. We'll claim it's optimal. Next lecture, we'll see a proof for this as a special case of another proof that we'll be covering. But the intuition here is that you explore everything that's reachable below a certain cost. And so nothing is left by the time you declare success, nothing is left that could be cheaper. Okay, so it's complete and optimal. That's good. The bad is that it explores in every direction and uses no information about the goal. So let's take a look at what that means in terms of exploring every direction. Quit this. So here is on our empty grid again, uniform cost search on our empty grid looks like this. Since it has no notion of where the goal is, it expands equally far in all directions, and so it could spend a lot of time going in the wrong direction. Next time we'll see how to avoid that. Take a look at a different demo here. We actually still have 5 minutes left, so people can stick with this so we don't have to come back to it next lecture. So what we see here is a maze with varying costs. We'll look at different search strategies. You'll get to pick which search strategy it is. So let's first look at uniform cost search. Dark water is high cost. Brighter water is lower cost. What does uniform cost search do? As it expands, notice you see it slows down when it hits a region with darker water, explores the shallower water more quickly, and hence finds, in this case also, a path to the goal that's the cheapest path. Compare this to, let's say, a breadth-first search, which would equally fan out in all directions, ignoring cost, or compare this to a depth-first search, which would just go leftmost first. Okay, here's the last slide I want to cover in this lecture. We have seen the tree search algorithm. The key concept was the concept of a fringe. It's where you have the nodes that are still up for expansion. What differed between the algorithms was what you decide to pick from your fringe next. You could pick the deepest node, the shallowest node, the least cost node. That corresponded to 3 different strategies. But you can actually implement this all with essentially the same code. And you might want to do this for your project 1. You might have the same code where the only thing that changes in your code is how you pick things from the fringe to expand next. And so there's this one queue, a priority queue, that you could use where priority could be based on depth, higher depth better or lower depth better, depending on your strategy, or based on cost. And just changing that priority in your priority queue will change which algorithm you're running. All right, that's it for today. See you on Tuesday.